Hello everyone. So we are here to review the key concepts that has been covered, you know, in the last 3 weeks in this course, theory and applications in thermal and cold plasma. So the concepts that we have covered in this last 3 weeks, like this diffused and constricted arcs, then transferred and non-transferred arcs, arc root movement and inherent arc instabilities, then cathode and anode jet formation, electromagnetic pumping, implication of electromagnetic body forces, J cross B, plasma thrust. So these are basically, arc plasma devices related topics, and they really do have great significance in operation and understanding of these devices. So mostly you will encounter the arcs which are either diffused arcs or constricted arcs. Regarding mode of operation, either it will be transferred arcs or non-transferred arc. Then, if you want to manage the movement of that arc, you need to understand the inherent instabilities in the arcs and the way the arc root moves. Because as you know, the arcs operate in a regime where the current is actually very high and the arc root formation takes place in an area of several millimeter square. So if you are passing some current, say 100 ampere, and you divide that by the kind of area through which the current enters into the anode, several millimeter square, so you are dividing 10 to the power 2 divided by 10 to the power minus 6. So that is ampere per meter square. So it is coming of the order of 10 to the power 8 ampere per meter square. It is tremendous amount of current density, and you know that the heat that is generated, it will be proportional to J square by sigma. So it is proportional to J square. So 10 to the power 8 is J, and when you make it a square, then it becomes 10 to the power 16. So the thermal load at the point of contact over the anode becomes tremendous, and that is why you need to understand the movement of the arc root and the inherent arc instabilities to design a device so that you can increase the lifetime of the anodes. Then regarding the cathode and anode jet formation, electromagnetic pumping, there the fundamental aspects of the arc plasma devices. So this is mainly because of the current carrying nature of the plasma, and the current produces magnetic field, and the orientation of the J cross B vector that causes this kind of jet formation, and that also basically leads to electromagnetic pumping. So the J cross B plasma thrust can be manipulated in a number of ways to facilitate the process that you are going to cover using the plasma device that we have designed. Now next comes the RF plasma devices. There is a series of devices which also operate in thermal as well as in the non-thermal range. So these devices serve a very useful purpose in many of the applications. So we need to know the principle of this RF plasma generation that you have studied elaborately in the class. Then regarding the device design, special features that are required, and thermal and flow field, because this radio frequency, they get attenuated as they enter into conducting media, and the plasma is a conducting media. So when you are impinging some radio frequency electromagnetic wave, it gets attenuated as it enters into the plasma deeper and deeper. So if you want to couple electromagnetic wave with the plasma, you need to know the frequency, and then there is something called skin depth, which allows the electromagnetic wave to enter into the plasma, the distance through which it get substantially attenuated, it has connection with this skin depth. Now, as I told you that RF plasma devices can operate in the cold plasma regime also. So I will tell you the design and construction of some radio frequency cold plasma devices also. And these devices not only work in the radio frequency range, they can operate in the kilohertz and megahertz range as well. So dielectric barrier discharge and capacitively coupled plasma, this direct discharges. So these are some of the very important topics of present day's relevance, and they are now getting applied in many biomedical areas and synthesis of novel materials, because the low gas temperature of this cold plasma devices. So their discharge characteristics and distinctive features, so those things we have also studied in our regular classes, and they are very much important. So we will review some of them, the key features. Then comes the important concepts of thermal equilibrium. So as far as plasma is concerned, three types of distinct thermal equilibrium exists over there. So one is your complete thermodynamic equilibrium, CTE, then local thermodynamic equilibrium, so that is LTE, and then partial local thermodynamic equilibrium. So the concepts we have covered, and we will see which of the plasma in which equilibrium state. So we will review the key features in this lecture. Then when the plasma radiates, so sun it almost radiates like a black body, right? Now whether the plasma that we create in the laboratory, they radiate in similar manner like that in the sun, actually this is not so. You need some minimum volume, after which only this radiation equilibrium exists, and that allows the plasma to radiate like a black body. So laboratory plasma may have some continuum part, but that is not exactly like black body radiation. Then comes the determination of plasma temperature and the electron number density inside the plasma. Now there are two types, thermal and non-thermal. The methods vary in both the cases. Because thermal plasma, the gas temperature is very high, you cannot introduce any invasive probe over there. So what you can do there? You can do, non-invasive techniques like optical emission spectroscopy. Whereas in case of cold plasma, because the gas temperature is low, you can do invasive probe measurements like the Langmuir probe that we use for determination of cold plasma temperature as well as the electron number density. So, we will cover in this all these aspects in this review. So, first the concept of diffused and constricted arcs. This is a very important concept. So, in an arc plasma device, as we have studied in the regular classes, that there is a cathode and there is an anode, and initially you apply some radio frequency discharge, radio frequency electric field to initiate the discharge, and once you do that initial ionization, then the applied bias between the cathode and anode establish the plasma, and that plasma goes out. So, what just now we have seen, that is just a numerical simulation of this device that you have seen number of times in the regular classes. So, this is a 2D simulation. So, this is the axis, and on top part of that, so above the axis, what you are seeing here, this is a presentation of the electron temperature, and in the bottom part below the axis, what you are seeing, this is a presentation of the heavy species temperature, and you can see the distribution on the bottom and distribution at the top. They are distinctly different in the periphery, but not in the core region. So, in these thermal plasma devices, the core region usually is having the thermal equilibrium, but not the peripheral region. Now, the concept of this diffused and constricted arc. So, as I told you, say if you take a section and you just see from the side, then you will see that this is the cathode tip, and this is the this nozzle bore, and this is the anode part, this bluish one. Okay, and this cathode tip is symmetrically situated in the cavity of the nozzle. So, once one electron comes out from there, then the question remains where it actually enters into the anode, because all the each point over the anode at equal potential. There all the points are at equal potential. So, once the electrons comes out from here, so this cathode is negative and this anode is usually grounded. So, it will try to reach somewhere on the anode, but where it goes to 1.1 or 2.2, 2.3 or 2.4. The problem is that all of them are at same potential. So, the single electron cannot reach at the same time to all the points. So, it will reach some point. Okay. So, if the one electron reaches here, so the next electron that has been emitted, it may reach the other point, because all of them are equally probable. So, if you are handling a number density of there of say 10 to the power 21, 22, 10 to the power 23 kind of thing, then there are huge number of electrons which are coming out, and they will be mostly equally distributed along the periphery, and what you get a connection, electrical connection of this arc over the anode in a bell shaped form. Okay. So, when the arc is uniformly connected all over the anode, so that situation we called a diffused arc. So, obviously, what are the points to be remembered in case of diffused arc? That the current density is low, because the current whatever you are pushing, say 100 ampere or 200 ampere or say 500 ampere, if that is distributed over a wider region, like all over the anode, then what you get actually, the current density is total current divided by the area becomes less, because the area is very high. On the other hand, when you are looking for this constricted arc, what happens, that occurs in case of molecular gases and at very high current mostly. So, then what happens, this these electrons which are emitted from here, they really do not reach every point over the anode. So what they prefer, they come to a particular point over here because they find some least resistance path through which they proceed. Now once the current is bit in this region, then they hit this region only and they do not hit the other regions. So conductivity becomes more in this region only. So more electrons prefer this path to enter into the anode because they are the least resistive path. So once some instability or other makes the current to shrink to a particular location, then that situation gradually worsens, and finally you get only a point over which the arc attaches. So that condition we called constricted arc. So as far as arc operation is concerned, diffused arc and constricted arc are the concepts which needs to be kept in mind. In case of diffused arc, it is very easy to manage the thermal distribution, thermal load distribution over the anode because the current density is low. But in case of constricted arc, because the arc is entering at a particular point and the current density is very high, so it can melt the location where it is entering. Fortunately, there are certain inherent instabilities that doesn't allow the arc to stay at a particular point and it roams here, there like that, but still stays in a constricted form only. So because of that inherent movement over the anode at various parts, the heating of a particular point doesn't continue for a long time. So that this melting of the anode location where the arc attaches get limited. Otherwise, it will not take much time to perforate the anode completely if the arc continues to stay with that high current density. As I told you, it will be of the order 10 to the power 8 per meter square, and in just few minutes it can perforate the wall of the anode and puncture the device. So structural integrity of the device get endangered. Now, transferred and non-transferred arc, this is another concept where these are the kind of situation. There is cathode and this nozzle, or you say anode. The arc is established between these two, and the gas which is passing through getting heated, and a plasma jet is coming out. So plasma jet is rather current free in this case, and the job on which you want to apply this plasma jet, that is outside here, and no electrical connection there with the job. So these kind of configurations are usually used in case of thermal spray devices where you inject some powder over here and that get melt and that gets sprayed over the job, and the job get coated with the high temperature refractory material, usually some ceramics, get deposited over the job. Now the other case, when the arc is directly connected to the job, that type of connection is called transferred arc. So earlier one was non-transferred because the arc is not transferred to the job, and in the latter case the arc is basically this red zone you just follow, so that is connected to the job. So when you are basically applying these arcs for cutting, for example, then you really want the current to enter into the job so that the heating continues in the plasma. So ohmic heating continues as long as the current path is there. So it is heating the plasma jet till it touches the job and the temperature becomes really high. And these devices for cutting, they are made in such a way that the current density here make the plasma to reach a temperature more than 20,000 degree Kelvin, and that's how the cutting torches gives a cut quality which is almost comparable to the laser cutting. So these are the concepts of non-transferred arc, and this is the transporter. Now coming to the electromagnetic pumping, cathode and anode jet formation, these are two processes which are very much relevant when we are designing a process and we are using the current carrying arcs. So here you go actually. So what you are seeing here, that is anode. So electrons are entering here. So current direction will be just the direction of the J that has been given here. Now you know, so the upper region is having a very high temperature zone, and this anode usually water cooled, and the arc get constricted over there, and then it diverges and enter into the bulk plasma. Okay. Now because of the specific diverging configuration of this current density, the magnetic field that is produced by the current, they make a configuration of J cross B, that will be here in this case, in which direction? In the upward direction. Okay. So this will be perpendicular to this J and this B, and you can consider the surface. So the vector will be right in this direction, and it will have one component in the upward direction and one component in the horizontal direction. The horizontal components will cancel each other, and the vertical components will be there, and that will create a body force which will push the plasma in the upward direction. So these arrows are showing that thing. Once the plasma is pushed in the upward direction, the vacuum created over here that pulls the plasma or the gas from the surrounding into it. So what is happening? They are collecting the gas from the surrounding and pushing up, collecting the gas from the surrounding and pushing up. So that is causing formation of strong anode jet, and this is actually photograph of that we have recorded when we are doing some underwater cutting kind of thing. So this is the anode, and the arc has entered here, and the anode jet that you are seeing here, it is just a physical photograph of the phenomena, and the jet goes like this. So you can see that thing. And now this is the anode jet formation, and now I will be talking about the cathode jet formation. So as I have told you that there is a cathode, and this is the anode part, the black one. Now what happened, these are the current density vectors. So at the bottom, suppose this is a cutting touch configuration, so current is entering there, rather the electrons are entering there, so current direction will be opposite. So this is the current density vector, as you are seeing, it is going there, and then they are taking a turn and entering into the cathode tip. So the J direction here is like this, and B direction is like this, overall B direction, and J cross B direction is bit tilted like this. And now we will have again two components, one is towards the bottom and another will be towards the radial inward direction. So the radial inward component will cancel each other when you consider the whole circle, and the resultant component will be in the bottom direction. Now in the downward direction, whatever the J cross B component is there, that will push the gas in the direction towards the bottom, and that will form the cathode jet in exactly similar way as the anode jet was formed. So these are the mechanism of formation of cathode jet and this one for anode jet. So these two phenomena basically controls the fluid dynamic and thermal field distribution inside the process zone, because there will be cathode, there will be anode, and they will form sometimes this cathode jet, and because of the electromagnetic body force, the velocity distribution of the charged particles within the process zone will be altered because of this jet formation owing to the J cross B body forces. Now this J cross B body force can be utilized in a very innovative way to produce very large volume plasma jet. In this, we have shown one. So here what is happening, this is the cathode, and this current is entering into anode. So actually if you put the direction, so that goes like this, opposite to the direction of the movement of the electrons. So this J is coming like this, and then it is crossing over here and then entering into the cathode. So this zone is basically the plasma jet, and it is having lots of electrons and ions. So when there is a potential difference, the current does not pass through a particular region, rather there is a broad region through which the current passes, the current density vectors you are seeing here. So in this whole zone, the some or other current is passing, and that is here horizontal. Okay. And what is the direction of the magnetic field? Because of this vertical current, so that is entering into the page, and this is the direction of the J in this. Look at this circle. So J cross B, if you put, you just apply your right hand rule, and you see that the thrust is straight away downward. Okay. So that thrust is causing this plasma jet to extend so long in the downward direction. So the reason for production of this so large plasma plume is the J cross B thrust that is produced inside this plasma jet because of this kind of current configuration. Now I told you that from the cathode jet is forming, and it is coming out like this, and the electrons are finally entering into the anode. So this is the region. Now I previously also shown you this video, and it is very important to know that current is entering in the anode, and it is entering into a very, very thin zone of a zone of very small diameter, and that is why the current density is increasing, and that is why the heating is so high over here and is so luminous. So this luminous zone, so the zone called the arc root, if that stays at a particular point for quite a long time, it will melt the anode. So this zone, what is in the periphery, this is the anode, and cathode you are not seeing here, it is bit deeper. Now from there, the jet that is coming out, you are able to see. So this is the cathode jet, and this is the point where the arc is entering into the anode, and that is called anode arc root. Now it is important to know inherently whether the arc root stays at a particular point. If it does so, then it will melt the anode, and if it doesn't, then the anode will be saved. So you see that how the this arc root varies. So initially it was here, and you see that now it is moving, and this is the current path, and the arc root also is not staying at a particular point, it is moving here and there, and sometimes you will see that two arc roots being formed. Here you can see that another arc root is being formed, and this root is not staying at a particular point. So having this idea, this concept that the arc root, this is the arc root, this is the arc root over the anode, and sometimes two arc roots are staying simultaneously, so they are dividing the current density again. So you see here, one branch is over here through the outer region, and one branch is very close to the cathode. So the current is divided, but the J cross B thrust is produced over here because it is making a U-shaped structure over here. So you now can see the U like this, okay, and here the thrust is being produced, and that is causing the plasma jet to produce so long jet. So I will take a short break now, and we will be back again in the next class. So thank you for your attention.